Morning, everyone. So far in this chapter, we've been mainly looking at the rate of a reaction. It's the speed at which you form products versus time, or it's the speed at which the reactants themselves get used up. Yesterday, we started looking at a guy called collision theory. For a successful collision to occur, there's two requirements. I'm going to give you a quick practice question for you to study that there. And then, in case they suggest to you a changing a factor, oh, I heat it up, or I cool it down, or I add more particles, you should be able to use collision theory to actually explain why that changes the rate. So, just for a quick warm up here, and then we'll get into a little bit more math in today's lesson. So, for a warm up, I want to know, as I alluded to here, state the two conditions necessary for a successful collision. So I'm already implying, yes, I know particles have to collide, but for a successful collision, this is for the reaction to occur, for it to actually get to go from reactants to products. And then two, I want you to sort of use those reasons. So using collision theory, using what you state in part A, using collision theory, explain why reactions, I'm just saying RxM for short, reactions are generally, there's always going to be exceptions, generally slower at colder temperatures and let's say lower surface areas. Right? And you can explain those two separately. Again, I encourage you just to pause the video, try it out for yourself, make use of the kinetic energy graph and the potential energy graph, and see if you can go from there. Assuming you've done that here, let's state the two conditions. For a successful collision, it always comes down to these two things here. Particles have to have sufficient energy. There is an activation energy that you need to actually overcome. Sufficient energy to overcome the activation barrier. You can just say the sufficient energy part of it. Basically, there's a limit, there's an energy hill. If you weren't traveling fast enough to begin with, you will always trade kinetic for potential. But if I wasn't going fast enough, by the time I trade my potential, I haven't quite gotten enough to actually get over the hill yet, so therefore no reaction. The other one here, especially in helping to explain arguments like surface area here, we need to talk about having favorable geometry or a good geometry. I've seen this written in a couple different ways. You can talk about the orientation, sort of the angle at which it comes in, the angle of hit. There's a couple different ways of saying that there. And pretty much when we sketch our potential energy diagrams, the activation energy barrier is already big enough. It's already assuming the best case scenario, the best geometry here. All right? So they give us these two factors here. We're looking at temperature and we're looking at surface area. Just ask yourself, have we affected the energy? Have we affected the geometry? Just a nice hint for you. The only thing that's going to affect the sufficient energy argument is temperature. What's going to happen to this kinetic energy distribution graph as I affect temperature? So kinetic energy distribution graph has the number of particles at any given time, plots against kinetic energy. Remember, that means we have slow particles, and then we steadily get to faster and faster moving particles. The distribution always looks like this. So even though on average, most of the particles are traveling at some medium pace, there is an activation energy requirement. There is a minimum amount of energy for the reaction to occur. So I plot this against potential energy against our reaction axis. I don't know endo or exo. So there is an energy requirement here. If I actually figure out the size of this hill, again, that already assumes the best case scenario, the best geometry, we see that it's only the particles that have fast enough, high enough kinetic energy that can actually react. Majority of particles can't actually react. What's going to happen here is as I steadily make the box cooler and cooler, well, the particles themselves are going to start slowing down, the average energy is going to slow down as well. Eventually what's going to happen is I'm going to get even fewer particles. So it's going to be shifted over something like that. Sorry, I'll make my curve look a little nicer. What I want to emphasize to you here is the activation barrier does not change. The energy requirement for you to break those bonds, for you to form that species called the activated complex, that part there has not changed. But you actually notice as I get colder, the blue curve here is a little bit colder. We use the rule of thumb here, every 10 degrees, it had sort of doubled the number that was beyond the activation barrier. In this case here, I don't specify the 10, it's just sort of in general cooler. As you're just doing your explanation here, I would emphasize although the activation barrier remains the same, it's the same bonds that we're trying to break. It's actually because we have less particles with enough energy to overcome the barrier. So the energy requirement hasn't changed, just we have even less particles that can actually do it, that can actually get over this hill here. Yes, in the sort of mirror image of what we did yesterday, yes, when you cool it down, there's also going to be less collisions, but it's not as big a problem. Less collisions does amount to less successful collisions as well, but less collisions is not as important as a reason. Right? So not just, oh, it's colder, there's not as many collisions. At any given time, even if we're at a really cold temperature, negative 10 degrees, negative 20 degrees, there's still going to be collisions on the order of thousands of collisions, tens of thousands of collisions. But the more important one here, I'm going to highlight for you here, it's less particles with enough energy. We're using that enough energy argument to actually explain it. How about for lower surface area? For lower surface area here, I'm not touching the energy argument. I haven't cooled it down. I haven't shifted the curve. The curve is identical. The energy requirement is identical as well. But let's imagine sort of the opposite from yesterday as well. Let's go from a case where everything is nice and shredded and nice and exposed, and let's actually put that back into a chunk. As I put that into a chunk, essentially what I've done is I've actually hidden some of the particles inside. Because I need collisions to occur with the right energy, with the right geometry, it really is only the outer particles that can actually do the collisions. So for the second reason, for the lower surface area work, we're actually not looking at energy at all. For lower surface area, we're going to say we have less particles exposed to collide. So this time, we can say, yep, there's less collisions. I haven't touched the energy argument. Don't just leave it with less collisions. Also mentioned here, there's lower chance of a good geometry collision. There's a lower chance that the particles are going to come in with the correct orientation so that they can actually react. All right? So those are some of the key ideas we looked at so far. Collision theory is going to come back again and again. And all we're going to start doing over the next 2 lessons or so is we're going to start introducing a little bit of the math. So if you can just flip over to your notes here, today we're going to learn this rate expression, or a rate constant, also referred to as a rate law. Essentially, we want to do it a little bit more quantitatively here. As I change those factors here, can I actually experiment with how quickly the concentrations end up dropping off? So as we step our way through here, changing the concentration of substances taking part in the reactions usually changes the rate of reaction. I want to emphasize for you here, when I look at a forward reaction, let's say reactions become products. Let's say the forward reaction, so let's go FDW. The forward reaction only depends on the reactants. It depends on whether the reactants have enough energy, whether they're coming in with the correct geometry or whatnot. I could care less what the products are. So the rate only depends on reactants. So that actually gives us a nice, just even starting question. Well, if I have many different states here, I would expect solids, well, they're going to be slow, right? Particles are sort of locked away. They're just vibrating in place here, really low energy. The chance of them colliding at first is already hard, but even if they did collide, it's a really low energetic collision. Solids would tend to be slower than liquid reactions. Liquid have a little bit more energy. They're starting to slip and slide past each other here. More collisions, better chance of a good geometry. That should be, next up is going to be gases, right? Even more energy than before. Surprisingly, however, this is more so from grade 12. Surprisingly, we're actually going to have aqueous actually faster than gaseous. That's, again, it's a generalization. But basically the idea here is for an aqueous, so we're still in solution. Unlike a gas which is completely spreading out through the container, at least all the particles are still in close vicinity here. The advantage of being aqueous for being dissolved, I have charges, maybe A is a plus and maybe B is a minus. In addition to just random orientation, random hitting between A and B, maybe it's this positive and negative attraction that's actually going to pull A towards B, and that's actually going to allow the correct particles to collide together with correct orientation. Usually they find aqueous is a little faster than gas. So if you have nothing else to go on, I would just generally have that order here. Solid reactions here, I'd expect it to be slow, whereas gaseous and aqueous are expected to be fast, and we're only looking at the states on the reactant side. Okay, so we're going to introduce a little bit of the math here. When they asked you, can you state the rate expression? What they're asking for here is, can you give me a mathematical function that expresses the dependence. How does the rate change? The dependence of rate on the concentration of the reactants. Again, the emphasis here is, yes, we want collision theory, yes, we want good energy, good geometry, but it really is only the reactants that need to collide. You can produce a product that's a solid, it doesn't suddenly slow the reaction down. So let's consider a very simple reaction here. A and B are supposed to collide. They're in aqueous. That's already the fastest state here. The forward rate will only depend on A and B. What the rate law is going to do is it's going to give you a way that your speed is going to depend on what concentration of A. Is it to the power 1, to the power 0, to the power 2, whatnot. What's super important here, make sure you take this note down. These rate expressions are also called rate laws. Rate law can only, let me put this in capitals here. Rate laws can only be determined experimentally. Right? It's going to be really tempting. Oh, wait, I have coefficients in the balance equation. It's a 1-to-1 ratio. Shouldn't it be to the power 1 to the power 1? We'll just take it for time being. You can't use stoichiometry here. Only determined experimentally, not necessarily from the Stoich coefficients. Okay, so I'm going to hint at how we're going to set up the experiment, how we can actually collect data to get it experimentally, but pretty much you cannot just look at the numbers. What's troubling here is in our second chapter, we're going to do an equilibrium law. Those ones there, we can use the coefficients, and that's where people get really confused. So at least for chapter 6 here, these can only be determined experimentally. So let's just take it for the time being, and then we'll explain why in tomorrow's lesson. One possibility is your rate, the speed of the reaction, how fast your product increases or reactant decreases, is proportional to A. So therefore, I'm going to use the terminology here. This one here is first order in A. So if you double A, the rate is suddenly doubled. If you times 3 by A, it's going to times 3. It's just proportional. Or the rate could be proportional to the square of the concentration of B. So we can say in that term here, we can say it's actually second order in B. And pretty much the order refers to what power that we're actually raising it to. It could be proportional to both A and B. So you change A, it's proportional to it. You change B, it's also proportional. So in this case here, you can actually say it's first order in A and B. And you'll notice in all these sort of examples here, it didn't have to match to the coefficients. It could have been 1, it could have been 1. Oh, it could have been 2 in B. That's fine. It doesn't necessarily need to match with the Stoich coefficients. So as a generalization here, for the general reaction A, B, and C, we are only focusing on the reactants. It's just these guys that need to collide. I could care less what the products are. I want the dependence between rate. The rate on this side here is the actual speed. Right? Remember, we had defined rate here. This one here was the increase in products over change in time. So if you want to look at your units here, the top unit here is going to be mole per dm cube per second. So really fancy set of units here, but it pretty much is how much product do I form or how much reactant is getting used up. How does the speed change? We're talking about this whole notion of proportion. So there's going to be a proportionality factor. We're going to call that K there the rate constant. So rate constant. That's going to depend on which exact reaction you're doing, what are the conditions, like what temperature you're at, a whole bunch of ideas like that. Because we're interested in A, B, and C and potentially more chemicals colliding, we're going to have A, B, and C just sort of listed in order. All of these ones here might have some impact on the rate. And what I'm going to raise it to is I'm going to raise it to the order, you can say X, Y, Z, you can say M, N, O, it doesn't really matter, right? And dot, 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 right? So this is called the rate law. It's trying to get a mathematical function. How does your speed of that reaction in molar per second, how does it depend on a proportionality constant, and how does it relate to each of the chemicals? Maybe it doesn't depend on concentration B. Maybe it doesn't depend on concentration C. Maybe it depends on A squared. How does it experimentally depend on? So just some phrasing here. We're going to say where the order of reaction, so far we've done sort of first order, second order, something like that, where the order of reaction so far, based on how I've listed, the order reaction, we can say it's X in A. Right? If X was 1, it's first order in A. If Y is 2, it's second order in B. So it's Y in B. And sometimes what we like doing is we actually like putting it all together. We can ask you for an overall order of the reaction. The overall order is the sum of the individual orders. So orders is just another name for just those powers there. Let's say I really only have A and B, so therefore the overall order would be, let's say, A plus B, right? Oh, sorry, X plus Y. So sum of X plus Y plus any number. So if, for example, it was first order in A, first order in B, I may be second order overall. Right? They're giving you some definition here. K is known as the rate constant. K does not vary with concentration. The whole reason I listed it out this way, I want to deal with the concentration aspect separate from the K. It doesn't vary with concentration. However, it does vary dramatically with temperature. We'll come back tomorrow and we'll talk about an Arrhenius formula. And this one here will further explain why when you heat things up and cool things down, why things are sped up or slowed down, respectively. Therefore, it's always important to state the temperature because the K might change. And if you change the temperature, your K is going to be different. What's really weird here is you're going to notice the rate is always going to have units molar per second. Depending on what the concentrations themselves are measured in, each of these concentrations are going to be mole per decimeter cube. But depending on the order, I might end up squaring the units to the power 3, the units here. K is basically going to have a different set of units to cancel out whatever units are in that particular rate law so that the rate eventually can be in molar per second. So let's just do this here. Experimentally determine the order. Let's imagine our simple reaction again. A and B is supposed to become C and D. Again, I don't care about what C and D are. What we're going to do here is we're going to set up an experiment quite cleverly here. We're going to keep all other factors. Right? I have too many unknowns in this problem otherwise. Keep all other factors constant. I want you to consider just taking turns. Let's start off with A. That was our first chemical. Consider doubling A. Right? I could have tripled it and whatnot. Right? Times 2 is just a little bit easier to do. If, by doing that, if the observed rate, right, so you knew what the rate was before, you double A and you just watch what happens to the rate, a couple things could happen. First thing is there was no change in the rate. So maybe our concentration of A used to be 1 molar. I knew the speed was 5 grams per second. And then now you double it, let's make it 2 molar. Now the rate is still 5 grams per second, right? So in that case there, if there was no change, that would sort of imply maybe we are 0 order in A. Because what would happen here is, even in the rate law, I have a general rate law here, I have A and B as my only 2 chemicals. Even if I doubled, if I times 2 by A, if there was no change in the rate, it's maybe the X is 0. So that anything to the power of 0 just becomes a 1, and that actually doesn't change the rate here. So mathematically, I'm doing like 2 to the power of 0, it's 1. You can double it, you can triple it all you want, nothing really happens, fine. Other things could happen. Again, this has to be done experimentally for each particular experiment. You can't just look at the stoichiometric coefficients. What if by doubling A, your rate is actually doubled? Right? To what power does A have to be so that when I multiply by 2 the actual number of particles, suddenly the rate also doubles? Well, that means the X, the order in A, has to be to the order 1. Because 2 to the power 1 is actually 2. You double A, that's why rate actually doubles. So rate is doubled here, we can go first order in A. Or a couple other cases here. Let's say your rate is multiplied, or it's increased by 4. Right? So again, all I'm doing is a constant. All I'm doing is I'm doubling A. When I double A, I just want to see what's going to happen potentially to my speed, and this time what ends up happening is your rate ends up timesing by 4. Well, wait a second, I only doubled A. What order, what power do we have to be so we actually double like that? Well, 2 to the 2 would mean times 4. You notice by keeping all the other factors constant, I'm keeping B the same. I don't yet know what the order is in B. Once I know what A is, I can then do a similar experiment. Let's double B and let's see what the impact on B is. K is going to depend on temperature. I'm going to assume temperature is constant unless they tell me otherwise. And if we're told the temperature is changed, we can actually figure out what the units would be and what the rate would be. Let's do one more here. So in the word here, we can say it's actually second order in A. You'll notice that the order is the name for the power, and it's also the specific to that particular chemical. What if in part D here, the rate is multiplied, it's scaled by 8, right? And now you get the idea here. Well, 2 to the 3 is actually 8. So if we were actually third order, even though the Stoichiometric coefficients may really well be 1a and 1b, that's why I'm telling you here the order actually doesn't depend on these Stoichiometric coefficients. You have to do it experimentally. Now we can actually say it's actually third order. And usually, if you just sort of work through this math here, again, doubling is nice because we can usually recognize, oh, it's times 2, times 4, times 8, something like that. You could have tripled, right? If I times 3 the A and I find that rate is tripled, it's still first order because 3 to the power 1 is still 3. If I triple it and then suddenly it goes up by a factor of 9, well, that's just 3 squared. I know it's second order. It's just doubling is a little bit easier because I can recognize those orders a little bit more simplistically, right? So let's work through a numerical example here. We will do exactly this setup as a method of initial rates one page from now. But what they want you to do first is just practice. Let's say we actually know some of these numbers here. How would we end up finding k? This is sort of an after the fact thing. I would usually do this as a last step. But let's practice to do this calculation first. Okay. So they tell us we're at 25 degrees. The rate of the above reaction, this is the speed. Okay. 2.5 times 10 to the negative 7. They have the units molar per second. If the reaction is first order in A, so when I write this rate law, let's start off here. The rate is supposed to be proportional through A and B. A is to the power X, B is to the power Y. I've seen them do M and N. It really doesn't matter what you label those. Remember, the rate only depends on the reactants, so I don't need to have the concentration of C or D in this case. This time, if the rate is 2.5 times 10 to the negative 7, if the reaction is found to be first order in A, so if I know X is equal to 1, and it's also first order in B, so that Y is equal to 1. They even give you the concentrations. They give you the experimental numbers here. My concentration is actually 0.015. The B is a totally different chemical, so its concentration can be way different. You'll notice pretty much I have all the variables. I just don't know what the K is. And they're asking for the overall order. The overall order is the easier one. So overall order, it's essentially going to be X plus Y. And in this case, they already told you it's first order. So the overall order is second order overall, right? So second order. It's first order in the A and the B. And what I can do is I could just rearrange this expression here. Since this is a function, I can just pull K is actually equal to the rate divided by A to the power 1 and B to the power 1. K is the constant, it's the proportionality factor. We are specifically doing the K at 25 degrees. This is going to stay true regardless of how your concentration changes later on. But let's try punching through the numbers. The rate is 2.5 times 10 to the negative 7. I'm going to keep track of the units here. This is going to become important very shortly. So that's actually the speed. The actual concentrations we're at this point here is 0.015 for A. That's to the power 1. 0.0075 to the power 1. These ones here are both in molar. They kept the units pretty simple for you because we're to the power 1. It's just molar to the power 1, not molar squared. So I'm going to type in the numbers. 2.5 e negative 7 divide 0.015 divided by 0.0075. I'm dividing by the specific concentration at this moment. Using sig figs here, I have 2.2 times 10 to the negative 3. Now, a question on units. Well, for our units, what we have, on the top, we had a unit molar per second. On the bottom, we had molar times molar, so we had a molar squared. You can think about doing sort of reciprocals here. Molar per second, it's multiplied by 1 over molar squared like that. If you need to show your work like that, you can. And then we're just going to basically try to figure out what does the K have to have units so that it can cancel all the other units I don't want and leave you with the rate in actually molar per second. So I see that one of the molars cancel out. My unit is actually a strange combination this time. It's going to be 1 over molar and seconds like that. So really what I want to say here is I want to have 2.2 times 10 to the negative 3. It should be molar to the negative 1, seconds to the negative 1. However, I can rewrite that a little bit here. So molar to the negative 1, seconds to the negative 1. They're both 1 over. The molar by itself is mole per dm cubed to the negative 1, seconds to the negative 1. The negative 1 just means flip the fraction. When I flip this fraction, this becomes decimeter cubed divided by molar. And I have seconds to the minus 1. So therefore, I can have my units overall written. Decimeter cube mole seconds. All right. And what you're going to find here is not only this rate constant, this proportionality factor will depend on the temperature, you're going to find the units really depend on what the overall order is. As a general rule, K has to have the right units so that it can get rid of all the units, which regardless of what the orders of A and B are, it can get rid of all those units and leave you with the rate that's in molar per second. And as the orders themselves change, the units will then also change, so you need to do this work every time. Right? There is a nice shortcut for you later on, but we'll get to that. All right, let's go to part B of this question here. Concentration A was held constant, so let's keep A at 0.015. The concentration B was changed. The rate was determined to be 1.0 times 10 to the negative 7. I want you to calculate the new B. Because this is a mathematical function, so we now have the rate is equal to K, A to the 1, B to the 1. Those are not given by the stoichiometry. It was given because they told me experimentally first order in A and first order in B. This time, the speed is actually changed to 1.0 times 10 to the negative 7. All right? If you just sort of make a general comparison here, we used to be 2.5, and now we actually have a lower rate. But I don't really recognize that factor here. Well, I actually know the order here. I just want to just calculate through, because you know the K, this is now constant. You could have changed B however you like. This is 2.2 times 10 to the negative 3. We had already worked out the units, so they canceled out everything properly. The A was held constant. We're going to see that on the next page as well. 0.015 to the power 1. What is the new B to the power 1? Great, I only have one unknown, so I can solve it pretty easily through here. 1.0, 1e, negative 7, divide 2.2e, negative 3, give or take a little bit of rounding, divided by 0.015. Double check my numbers. I'm getting the concentration of B should be 3.0 times 10 to the negative 3. And because this one here is a concentration, that one there should just be in molar. All right? So what I want to emphasize in this setup before we get to the next problem here, K is a, we called it a rate constant. Rate constant only depends on temperature. So even though in this experiment, I actually changed B, you notice that the K actually didn't change. And also the units will also depend on the order. So the units will depend on the order, and we'll get a little more practice with this on the next page. This constant here is basically everything that might change the rate other than the concentrations. We'll come back in tomorrow's lesson on Arrhenius to actually figure out what that rate actually is. So 2 practice questions for you just to go over there. You can match it up to the answers. Again, you'll notice the units are going to be a little bit crazy. In this case here, whenever you see mole per decimeter cube, that's just molar per second. That's the unit for rate. In this case here, the rate, you notice that the units is actually a mole to the negative 2, decimeter to the 6, and whatnot. We'll work out that part on the backside. Right? That's one way of doing the problem. That's sort of the easier way because I already knew the concentrations. I already was told the order. What if I don't know the order? What we're going to actually do is something called the method of initial rates. They're still hinting at, here's the experiment, here's the comparisons I was making. There's no one right way of doing this, okay? But I'm going to show you how we're going to work through this. In this case here, I notice they're giving me my initial rate. They're giving me my initial speed upon mixing A, B, and C together. Because I have 3 chemicals, I would imagine my reaction is A and B and C becoming something. And remember, my rate only depends on the reactants, right? So let's start off with our rate law. Our rate law essentially says the speed of any reaction is going to be proportional through K. It's only going to depend on the reactant concentrations, A to the power X, B to the power Y, C to the power Z, right? And I don't know anything. I have way too many variables. What they're going to do is similar to what we did on that front side there is we're going to start changing the starting concentrations. I want to change the starting concentrations, and I want to see its impact on rate. By doing that, hopefully by keeping everything else constant, I can first get what these orders are. If I then know what the orders are, I can just plug into one of these trials here with the concentrations. Then I can do this work from earlier. Find the rate constant, change concentration, whatever you want here. I want to just emphasize here, even though I can emphasize, A, B, and C are all reactants, my mole ratios could very well be, 2 times A, 1 times B, 3 times C. I am not going to get my X, Y, Z from the stoichiometry. The X, Y, Z comes out of the math that we're going to do now. All right? So again, emphasize here, X, Y, Z, the orders, are not the stoichiometry coefficients. Okay, we have to do this sort of method of initial rates. So here's what we're going to do. In general, we're going to compare two different experiments. Compare two experiments where only one substance is changed. Either the concentration has doubled or tripled or something like that, so that if everything else is constant, I can see its impact on the overall rate. And there is no, again, I mentioned there's no one right way of doing this. It sort of becomes like a puzzle. Let's look at experiment 1 and experiment 2. Experiment 1 and 2 here, B and C are exactly the same concentration. The only thing that I did is I actually doubled A. So that's my factor I'm doing here. I've doubled A, and I want to see what happened to my rate here. So let's go 9.72 e negative 3 divided by 4.86 e negative 3. That should give you here times 2. Sometimes you get like a times 1.96, something like that. Close enough, right? This is experimental, right? What I've done there is I've actually been able to figure out. So if the only thing I changed was A in this experiment, my change was I doubled A, and I found that the rate was doubled. What's the order going to be for X, right? You should be able to tell me right away it's first order, right? I doubled this, the other one doubled, it's to the power 1. I now know X, and if I now know X, I can use that for a future experiment as well. Just let me hint at what we're doing mathematically here. Mathematically, essentially when I'm saying comparing two experiments, I'm saying it's almost like do this rate law twice. Let's do the rate for experiment 2. That's going to be K, A times X, B times Y. You don't need to show this work here. I'm just going to show you in the background what we're doing. Rate of experiment number 1, I'm doing that as a subscript here. K, A times X, B times Y, C times Z. This is what you're doing in the background. I took the 9.72 number and I divided by 4.86 times 10 to the negative 3. That gave us 2. Fine. But because everything else is kept constant, I still have no clue what K is. K cancels out. The B concentration with its order, B to the Y, it's the same concentration, it's still to the power Y. This one cancels out. C is the same concentration, C to the Z, that also cancels out. I have no clue what Y or Z are, but in this case here, if I know the rate was doubled, that's because of just changing concentration A. A in this case here was 2 times what it was earlier. In this case here, it would need to be 2 times to the power 1 to actually do that. So mathematically, that's what you're doing. You're keeping everything else constant so that you can actually figure out what order individually they are. And as you figure out the individual orders, you can actually get more and more of your unknowns. So comparing experiment 1 and 2, you can do it for yourself. Comparing experiment 1 and 2, when A is doubled, right? I actually literally doubled that concentration, 0.4 to 0.8. When A is doubled, the rate is doubled. So that's 2 to the power what? Well, it's 2 to the power 1. So therefore, our conclusion out of there, we are first order in A. Right? So I've gotten one of them. This is from experiments here. Now notice maybe my Stoic coefficient was a 2 there. I don't care about that 2. The order in this reaction here is 1. Right? Let's keep doing here. What other two experiments can I actually compare to find the other two orders? Let's say reaction 1 and reaction 3. So you notice between 1 and 3, the A this time stays the same. The C is still the same. But this time what I've done is I've actually divided by 2 the chemical B. If you don't like doing the divide, you can actually start from experiment 3 and go to experiment 1. And you can say, okay, from 3 to 1, I've actually doubled B while keeping everything else constant. What happened to this rate here when I doubled B? In this case here, I know, wait, 4.86, it's the exact same number. The rate here actually times 0. So when I compared, again, mathematically behind the scenes, you're doing this. The rates didn't change. It was equal. It was a 1 there. The rate constant, I still have no clue what the number is. That canceled out. The A's were the same number, even though I now is power 1. Those ones there cancel. The C's also cancel here. I found that you double B, but the rate itself actually doesn't change. So let's compare here experiment 1 and 3. When the B is doubled, or B is halved, even if you like it that way, the rate is unchanged. So what order, what power do we need to take it at for the chemical B so that the rate actually doesn't care what the concentration is? You should be able to say to pretty easy, it's 0th order, right? It's no order in B. So even though my generic formula here, yeah, my reaction could have depended on A colliding with B colliding with C, based on this method of initial rates work here, we actually found that this y here is now currently 0. Definitely 0 is not your stoichiometric coefficient. So I again just want to emphasize, you cannot pull just the order of reaction from the stoichiometric coefficients. Right? So with that here, we actually know a lot. I know the x and the y. Let's just see if we can calculate through the z here. It's totally possible. Let's say I don't have an experiment that has like a and b constant and just c changing, but because we already know what the order in a and b are, I can figure out if the rate changes, how much is due to A, and then therefore how much is due to C. So in this case here, actually there's one or two ways I can do it. The easier way, if you don't want to do the method that I just mentioned, you can compare, let's say, experiment 2 and experiment 4. Experiment 2, A, B are the same. Those would cancel out. This time, oh no, I actually times 3. That's fine. Remember, there's nothing special about doubling. It's just easy to recognize powers of 2. If I triple this, let's see what happens to this rate here. So again, let's figure it out here. When C, this is one way of doing it. When C is tripled, when C is times 3, what happens to the rate? Let's actually type it in. Again, mathematically, behind the scenes, this is what I'm doing. 87.5 times 10 to the negative 3. They would usually write that 8.75 10 to the negative 2. Divided by experiment 2. Usually I go bigger number minus smaller number, so you can avoid fractions. 87.5 divided by 9.72 essentially, and this gives you 9. Okay, that's fine. I had actually times 3. 3 to the power of what actually gives you a 9. So therefore, we actually know that we're actually second order in C. So this one, because we're just starting off, they gave us a easy comparison where there was always 2 experiments I can compare. 2 of the variables were constant. There's only 1 that was missing. Let's say they didn't give you that though. So let me just give you another method. So I had found the order in C by comparing experiment 2 and 4. Another way you could have compared that, if I look at, for example, experiment 1 and 4 instead, right? You don't need to do this, right? But if you look at experiment 1 and 4, I've actually done 2 changes. B is constant. Not only is it 0, I didn't know that from before, but being is constant, it just cancels out. Notice what I've done is I've actually doubled A, right? And I've actually tripled C, right? Oh no, there's 2 changes. But again, because I already know what power it is in A, I can just sort of factor that out of the change. So if I more complicatedly compared experiment 1 and compare experiment 4 there, my rate between 1 and 4, again, you can do numerically here, 87.5 times 10 to the negative 3. This time I want to compare it to A, which is 4.86 times 10 to the negative 3. Just showing you a little bit more strategy here. 87.5 divided by 4.86. This one gives me, oh, it's 18. Oh, I don't recognize that as a power of 2 or a power of 3. But remember, we already found A was first order. So A would have been to the power 1. You have definitely doubled A again. So you've definitely times 2 to the power 1. Part of this factor change, this 18 multiple increase, the times 2 part was just due to the A. Let's ignore that part. A part of it, this was due to A. But what about the part that's due to tripling C? Well, I've dealt with the A, now I've tripled C here. The other part here, the times 9, had to be due to C to the power of Z. And in the same way here, I've tripled, so I actually times 3, 3 to the power 2. Again, you can say second order in C. So why did I do that? Sometimes they won't give you a perfect experiment where it's always, you have all the variables just doubling in 1, but sometimes you might need to do a little bit more puzzle work to actually get there. Now that we actually know a lot of the powers, calculating K is actually super easy. For calculating K, you can actually use data from any experiment. Right? I have 4 experiments worth of data. Use data from any experiment. I wasn't told that the temperature changed, so I'm going to imagine that they were all at the same temperature. Now what we found is our generic formula is rate is K, A is first order, so to the power 1. B is 0th order, so that dies away. C is actually second order, right? So we can clear this up a little bit here. K, A to the power 1, C to the power 2. And now this is my rate law. It was determined experimentally. It was not from the coefficients. Now what you can do is you can punch to any set of experiments. Let's say for argument's sake here, I plot through the numbers in statement number 1. So statement number 1 here, my rate was actually numerically 4.86 times 10 to the negative 3. The K I don't know just yet. I just went through this method of initial rates just to find my powers first, just to get some of those unknowns out of the way. But now I actually need to punch in A is actually 0.400. That's to the power 1. I don't need to bother punching in B. That actually doesn't control the rate at all. C actually is 0600 squared. You now see from what we did from the backside here, we can solve our way through K. So K is equal to, just divide it over, 4.86, I'll write it down for you. 4.86 times 10 to the negative 3 divided by 0.4. That one is to the power 1. Here's the C, the dependence, the order is squared. That's where it actually comes into play. 4.86 e negative 3, divide 0.4, divide 0.06 squared. This gives me here 3.38. Now what about the units? Okay, I'm going to do a simplification for you here, and we'll end off with this. The rate at the end of the day should be a molar per second, right? I now have two things, right? A is going to give me a molar. C is going to give me a molar as well, but there's a molar squared. So what's happening here is the A times C is actually giving you a molar cube. The unit for K has to get rid of enough of these molars just to leave you with 1 molar, and has to pick up a seconds. So for K, the units, I would say, K has to have the units, it has to be a meter squared on the bottom, because meter cube divided by meter squared will leave you with one of the molars that I want. Sorry, molar, not meter. And I also need to pick up a second, so my unit would actually need to be 1 over a molar squared second. Hey, wait, this is a different unit from before. That's because the order is different from the one from before. But if I just double check my work here, if my A to the power 1, C to the power 2, if that comes at me with meter cube, the meter cube would have canceled, 2 of them would have canceled, I keep saying meter, molar cube cancels out the molar squared. That leaves me with 1 molar and a second. That would actually be the unit for the rate that we need, right? So I checked it here. This is going to be my units. Usually it's not left like this. IB doesn't like this molar here. So what we're going to do is we're going to go 1 over. This is mole per decimeter cube, all squared, and seconds like that. Because it's 1 over a fraction, I can put the decimeter on top. The cube with the square is actually to the power 6. The mole squared here is just mole squared. And then we have seconds on the bottom. So you can actually write this out. dm6 mole to the negative 2 seconds to the minus 1. That's the easiest way to find the units, and the units are going to be contingent on what the orders actually are, right? So do practice through punching in through the data and actually making sure you're comfortable calculating K, calculating the units for it. And then, especially sort of more early on for a method of initial rates practice here, try doing this sort of experiment. Oh, if I double 1, what happens to this rate here? See if you can get the overall orders. Again, the confusing bit here is it's not necessarily going to be the coefficients. So they give you a couple different setups here. If they're nice to you, they'll give you 3 sort of combinations that there's only 1 unknown. If it's not nice to you, sort of the more information you know which part is due to A, you can figure out what part is due to the one that you don't know. Right? So I'm going to leave it off there. If you have any questions, just let me know. Thanks, guys.